Okay, we're going to continue on with the Fourier series. We're going to look at a couple of things. Let's first just remind ourselves what it is. So the Fourier series is defined by x of t is equal to the summation from k is equal to negative infinity to k is equal to infinity. So integer values over the entire negative infinity to infinity spectrum, or number line. A of k, e to the j, 2 pi divided by t naught, kt, or we can rewrite this and say k is equal to negative infinity up to infinity of a of k, e to the j omega naught kt, or we could rewrite this another way, the integral from k is equal to negative infinity up to infinity of a of k times the, oh shoot, I'm getting one step ahead of myself, I'm sorry. We're just going to go with two of them on there. Where, let me write this now, a of k is equal to 1 over t naught, the integral over some period of t naught, x of t, e to the minus j, 2 pi over t naught, kt, which is also equal to 1 over t naught, the integral over t naught, x of t, e to the negative j, omega naught kt, which we can also write this as one other form, 1 over t naught, integral over some period of t naught, x of t times cosine of omega naught kt plus j sine of omega naught kt. Alright, so now we have three forms of the a of k that we can work with, and we have two forms of the x of t. These k's, the k from minus infinity up to infinity, this is defined as the harmonics. So we're defining these numbers from negative infinity out to infinity. Each one of these is known as a harmonic. So when you hear somebody say the first harmonic, second harmonic, these are the harmonics of the Fourier series, the k's. The a of k defines the magnitude of the harmonic of the series. And in this third way of writing it, we can see that we can break the harmonics up into a real and an imaginary part based on Euler's equations. Alright, so let's use this a little bit to see what it does. So now, here's some considerations. Let's look at odd symmetry. Odd symmetry of x of t. This is going to be an equation such as a sawtooth. Alright, where it's passing through the origin. And this is, let's just define this zero crossing point as negative t naught divided by 2. We're going to define this one as t naught divided by 2. So there's the fundamental period. We're defining it as one cycle of the sawtooth. And that is the definition. The fundamental frequency is one cycle of the periodic signal. So, this is an odd function. Odd. So an odd function is one that is mirrored from this side to this side, or from this side to this side. So if at t is equal to -1, let's see, let me just define this. Odd x of negative t is equal to negative x of t. All right. What does that mean? This is really important when we're going to look at this form of it, because we have this cosine value here, and we know that cosine is also an odd function. It goes through the 0, and we have that negative form of it. So cosine, wait a minute, cosine does not go through, sine goes through 0. Sine is, getting all backed up now. Sine is an odd function, cosine is an even function. So cosine this is cosine of omega naught, and we're going to just go ahead and say omega naught of t. Okay, it's even. So now what do we have when we multiply an odd function by an even function? We can see if we take one value, such as this value, we're going to multiply the most negative number by the negative. If we look at this value, we're going to take positive multiplied by -1. So -1 times the negative, -1 times the positive. So these 2 points in an integral would cancel out, because they're the same magnitude except different sign. And if we go along and we say the product between the x of t and cosine of t, given the integral of that, we can see that each one of these values along this line will cancel out, because take this point, and that would correspond on this side to this one. The magnitude of both of these are the same. Magnitude of both of these are the same. All we have is a difference of sign. So, what does this mean? What do we care? So for an odd function, a of k is equal to 1 divided by t naught integral over some t naught period of x of t times, I'm going to use this last term, cosine of omega naught kt plus j sine of omega naught kt. When we distribute this through and do the integral, 1 over t naught is going to be the integral over t naught of x of t times cosine of omega naught kt. I need a dt. Omega naught dt plus the integral of t naught of x of t j sine of omega naught kt dt. This is the one that I was talking about. When we have an odd function multiplied by the even cosine, each one of these is going to negate in the integral. So this sum of the integral, the output of the integral, is going to result in 0 due to symmetry. Therefore, a of k is equal to 1 over t naught times the integral over t naught of x of t times j sine of omega naught kt dt for an odd x of t. we can make one more statement from this. So A of k is going to equal, not equal, A of k is imaginary. Imaginary. Oh, no. I'm just making sure I got it all right. So A of k is going to be imaginary for odd functions. For odd functions. Because we can see in this integral, we've got j. It's a constant. It gets moved out in front of the integral, so it's going to be odd. We can say one more thing about this. If we say that all values x of negative t is going to be equal to x of t, when we do this for omega naught or for the fundamental, which is the dc, a of 0, so not the fundamental, the dc, the integral of whatever's under this curve is going to end up being 0 because of symmetry. So a of 0 is 0 for an odd function. So these are the takeaways from an odd function. Alright. So if that's true for an odd function, what happens with an even function? So for an even function, so what is an even function? Let's consider a square wave. So here we have the value of negative t naught divided by 2 up to t naught. And for an even function, even is defined as x of t is equal to x of negative t. So now we can see that this guy has some DC content because he's raised above 0. So we can no longer say that a of 0 is equal to 0. But we can look at this same thing and we can say, oh, well, if this is now the sinusoid term, the sine term, it's now taking that sine that passes through here and it runs like this. And we can see that for every value on this side, there's a corresponding negative value on this side of the product of those two. Therefore, we can say that for even x of t, we know that a of k is going to be equal to 1 over t naught, the integral of t naught, x of t, times cosine of omega naught kt dt. So these guys become a lot more simple to find the a's of k's when they're even or odd. All right. So while we have this one on the board, let's look at one more consideration for this. When we have a square wave on the board, where'd that page go? We can go through and solve out the integral and find all the a of k values. And when we get these on a plot, they're going to look something like following. negative 3 pi, and then we're going to have 4 omega naught, and then this is going to be 1 divided by 5 pi, and then we're going to have 6 omega naught, 5 omega naught, this is 3 omega naught, this is 1 omega naught. Okay, and this would be mirrored on the other side. Okay, so the first one is called the fundamental frequency. It's at omega naught. This is the DC content. As we go off, we can see that the even harmonics are equal to 0 for this guy. The odd harmonics carry all the signal. So the even harmonics are always, let's see, even harmonics will all be 0 since an integral number of cycles fit within the square wave. Odd harmonics will be real since the sine terms cancel out for this example. Alright, so if we want to now do something where we apply a filter, this is where we want to look at what fundamental frequencies, what frequencies do we want to cut out of our filter. So we could apply a filter around this guy. It goes something like this, and cut out this guy. And these would go on, by the way. This would have an infinite number that continue to get smaller and smaller and smaller, and that's why it makes those sharp ears. So at some point in time, to make this into a real system, we've got to say, okay, how many of the harmonics do we want to keep? How many do we want to throw away? So we put some type of filter around it. And we could imagine this is an ideal brick wall filter, so it's just a straight down cut. That never happens in practice. But if we do that, we would take our square wave, put it through this filter system, and the output of filtering would look something like this, where we have the original, the output of the filtering I'm going to draw in red, would have a sinusoidal form. And this would actually come down straight there. Okay, so the red is the filter output. Filter output. And what you get are these ears. I call them Batman ears. The true term for them is the Gibbs phenomenon. So this is Gibbs. Gibbs. Gibbs phenomenon. So you get these distortions, but you can still see where the square wave is at. Now, this is really important because a lot of times in communications, ideally what we want to do is we want to pulse with a square wave on and then a square wave off, and then a square wave on and a square wave off. But we can't do that in practice because we have to cut off the higher harmonics because we can't have infinite frequency. So when we cut that off, it starts to get these ears. So this is one of the ways that we can do windowing. So we apply some filter to it, and it will distort the output, but in a known way. So, all right. I think that this is all we're going to look at for a review of the Fourier series. You should have seen all these in your previous class. There's one more video that I'm going to post about the properties of the Fourier series. And so that's it for this one.